All right, it's my pleasure to introduce Pham Tiep from Rutgers, MIT, and Princeton, who will talk to us about character bounds for finite simple groups.
Thank you very much. I like to thank the undergrad and also the owners of the senior Mario and George and other colleagues for inviting me to visit Northeastern. So like during my previous sub-article, so I was I was passing by train from Needham Junction to Harvard, and I can see the student Northeastern. This time I have to see it in my own eyes. Okay, right. So thank you very much. So I have to talk about the character bound. My second book. And so what is the problem that you want to study? So let's say that you have a finite group. Okay. And then you have a finite dimensional representation. So we need that you have a representation from your G into, let's say, some real and over C, the conic representation. And I'm going to assume that it's irreducible. So this means that you cannot put it in the standard log form. And also I'm going to assume that so the Tiep can be injected. So we are going to say it's spaceful representation. So then to this representation, you can associate this as a character. So the character W5. So it's going to be a map, say chi from the V into C now. And of course, so what you do is you take so the value of chi and every element is the choice of this linear transformation. Okay. Well, so we're going to talk about the bound of this value, and you can see that because your G is finite, so we can put this in the diagonal form, right? And the every diagonal entry is going to be a root of unity, right? So therefore, you can see that if you look at the absolute value of this, then you can see that is at most type 1 between with the n, right? Okay, and right, and roots of unity, right? And you can, because I assume that it's inducible and faithful, then you can see that we have the quality if and only if your phi is a scalar transformation, and so they mean that your G actually is the center of you. So this is by sure lambda. Okay. And you can see that the entire talk is going to be just about like can you improve on this inequality? Okay. So the main problem that we have to discuss is the following were the problems. So given V, well, to be precise, I should say it's a finite, and I put it in pattern is almost one simple, but maybe we can do it like simple, okay? And so the prototype is I mean just in like the GM and over F2, like and then this is over two element. So and if you want to know what it means that okay, so okay, quasi simple means that it's perfect, and the broken by center is simple, and almost quite simple means that the function by the center is an almost simple, but you don't have to care about that. Okay, so then I have a G an element in the group which is not in the center, so G is near the center of the group. So the problem A is that I want to find a small, let me say, an explicit and as small as possible the constant gamma, which may depend on your G, which is between 0 and 1, such that if you look at it, the ratio of chi G by chi 1, so we know that it's equal to 1, right? And I want this to be bounded by gamma. for all the time, I'm going to use the notation Theorem G to denote the state of all the characters of the user limitation of your group. Right? And of course, I mean, this is a fine problem. This is such a gamma, right? But the point is, I want to have something like an explicit formula and as more than possible. Okay. So usually people refer to this like the character ratio. So the ratio between character and the degree. And even better, if I want to find, okay, so again, I want to find an explicit and as more than possible alpha, which again may depend on your C and between 0 and 1. Such that chi of G. Now I want to have an exponential bound. So this means I want this to be at most chi 1 to the alpha power. Okay? And right. Of course, here I have to say that I want to look at the one whether it is left in 1 because if it is 1, then it is 1 here. But for this, then I can take the bigger factors. Okay. So let me go about the motivation. So why do we want to study this problem? Well, so the reason is that you see that if you can do that, so the reason is if you can solve it. So IOP then is going to be very useful for many applications. And usually this kind of application depend on or rely on the following formula, which is into Frobenius and the formula. So it says the following. So suppose that you are given this group G, right? A finite group, and then you fix an element, say written G here. And let's say that you are even with two coordinate classes. So A, the class of written A, so which is the set of coordinate of the A, and B is the class of written B. Okay. And now you want to count like the number of ways that you can write your G like the product of two coordinates from these two classes, fixed classes. So you need to count the number of pairs from a Y, where you actually in A, Y in B, and the product is X and Y. Okay. And the formula say that this is the same as the length of the class A and the length of the class B divided by the root of G and the sum of line A, line B, and line of G on this coordinate divided by line 1, and you sum over all the complex characters. Okay. And so you have this sum here, and of course, among the characters, you have the principal character, right? So the principal character gives you just 1. And you can imagine all the other ones, they give something you did negligible. So how negligible are all the other terms? This, so you can see the problem A from being intended. Okay. So both, yeah. And so let me give you some examples of this kind of application. So maybe one application is that like the Euler conjecture. So it says that in every finite non-reducible group, every element is a commutator. Okay, I think that the civil notice they are very good. So they are going to say that there are subgroup which are set of commutators. But for the other school, then they can make that mistake because for civil group. So this Euler conjecture say that is the same. It's not true for the civil group, but this was proved by Lee, O'Brien, and Charlotte, and myself, and the book like they have it on this kind of bound. The second application is about the random walk on telegraphs, and also we have the one notion which is the Mackay graph. So maybe at the end of the book, I need to come back to this. Okay. And maybe another application is about so you can view it like you could talk about random generation. Simple group, a finite simple group. And but this is another way to look at it, like you can talk about like representation varieties. So what you're doing here is that you have to look at the set of form from a group say gamma into another group G. So now here your G is like maybe the symmetrical, or maybe you can look at it like some if you can look at some simple element group. Like Theorem or something. Now gamma is a finely integrated group, and maybe let me just give you one example. So I'm going to talk about the function group in general, and then is so-called the Hermes group. So this is the group that's generated by three elements in x, y, and z, where x squared is going to be y cubed, equal to z is to 7, equal to x and y z. It has to be, need to be 1. Okay, so then you get, yeah, right. Right. And maybe there's also another application, which is about the conjecture due to John Thomson. And this is in open in German. So like you have to show that for any finite non-abelian simple group, say G, so G and it a conjugate class, a C such that your G is C squared, meaning that every element is a product of two conjugates of this fixed class, and this is a notoriously different conjecture. But anyway, so now of course if you well you know that I'm talking about the simple group and or almost simple group and so on. So like usually you have an SN, right? And you know the representation theory of SN very well, right? And you have the formula for the degree, the hook formula, and the hook rank formula, and they have the formula for the values, and you can compute it in different ways, right? And but then so how did these two things get broken? And even like for the group of B type, like or like something like GPRT, right? You also have like a very like probability and the book about the calculation of the GPRT, right? So it seems that we know a lot, but the point is even when you have a formula, then the formula is going to be having a lot of terms there, right? And even to find the asymptotically is tough. Okay, so so now let me try to
Can I ask a couple of questions?
yes.
So why don't you combine A and B into a single question about chi of G less or equal than gamma times tau for power of chi of 1?
Yes, you but you see that for some problem you want to know the okay. So for instance, like let's talk about like G and Q, right? So you see that you have a formula where indeed you have a term in here and then you have this, but you can do it like the first term is like something depending on the rank of the group, and the second term is can grow with your Q, and then you have to control that growth in terms of this alpha. Okay.
In connection to the Frobenius character formula and the Thomson's conjecture, is it known that G is always a product of two different conjugacy classes?
Okay.
Or that's all?
So the problem that okay, so this is like there is a lot of that. So you go the approximation of the Thomson conjecture, and you can see that when you have the product of two classes, right? Then you want so you want to have the identity. So the answer is if you read in your book and you allow me to show away the identity, conceivable that I can do it. Because but once you want me to have the identity, that means you want the x times y. So you mean you put a base on some constraint on the A and B. So A has to be the class something and B the A inverse. And that's make it much harder. So that's
And that is not known.
not know, right?
Okay.
And maybe at the end I'll tell you what we know what is, yeah, right. Okay, so so let me talk about some result on problem A. Okay, so really the best known result is the theorem which combine many papers of David Block. Also Block with Maharat, and this is improved and improve popularity. So that the three and myself, which we say that so let me put it this way. If your G is not something like Sn or An, symmetrical and the other rule, then in A you can take gamma to be something like 0.98 simplified. Now you think with them say, well, obviously it's less than 1, right? and then we have, I mean we had to work so hard to get 1% cheaper than that one, right? So but okay, but the thing is, even though it's so close to 1, but you cannot do much better than that. So let me give you one example. Let's say that you take your G to be the one who has right? Okay, then and you look at the reflection representation. So dimension 8, right? Right, and this is a reflection book. So you look at the reflection, they have the -1 and 117 times. So therefore, the value in what you get, the calculator is 6. So you see that the ratio here is 3/4, 0.75. That's it. So yeah, so that only shows you that you cannot do much better than this. But of course, this is not. I mean, this is how it comes up on the proof. I don't think that every example comes to this, but this like probably one is the best. Like one of the best values I can get.
And you're considering overall G
Yeah,
in the
yeah.
center.
Right,
So you're varying over both chi and
Right.
G.
So over on the group and over on the G. Yeah, that's why this is the uniform bound. Yeah. And you can already from this example you see why I have to throw away the SN and AN. Again, you can look at the reflection representation for SN, right? Then you get something N-2 over N. It's gonna be getting close and close to N. You cannot find away from N. That's what why. So that's why you have to go this school. Okay. But also related to this, and you can see that. So let me put it like so. If you look at the data that you have, if you work with gas or magma, or maybe you look at something you put the red line on the other supply symbol book, then you can have a lot of kind of table. So we have all this data for the symbol book, and then you can see that. So one thing that you can make is that the conclusion is that let me put it the father is away from the center, meaning that it belongs to the center, the smaller gamma can be, right? Okay. And so let me quantify this statement. So for most of the talk, I'm going to talk about the G like the classical, classical. So we mean that you have a finite vector space over Q, and then you have some so this could be like a Theorem, or maybe as a vector linear rule. You can do you have a symmetric form, or maybe you have a Theorem form and so on, right? Okay, on this space, and then you look at the center, the group of the isometries of the form. Okay. Then let me say that so let me change. Let me take the product with the color of the field, and then let me give you like a measure of G being away from the center. So let me define it to be the support. So the support of G. So this is going to be just the full dimension of the larger eigenspace. So you can look at the minimum over all the lambda in F2 bar. And then you look at the codimension of the current of the eigenspace on this space here. Okay. Right. And then when once you have this, then okay, so let me try to write it. Then we do have a theorem which will give you a bound on gamma, like which depend on the support. So this is a theorem which is due to Michael Larson and HRF and myself. So we say that if you G is like this plus group over the few element, then you can show that chi G or chi 1 is then bounded by something depending on your Q and on the support. So what you have in the bound is that you have Q to the power of the square root to the support of G, but then you have to divide by something that 481. So let me make some comment about the result. So first of all, 481 is something that we obtain in the proof, but it can be improved. But the thing that we are mostly unhappy about is that we have the square root here, where the data show that we should have some bounded linear in the terms of support. So okay, so the question is, can we check a linear operation? Okay. And maybe at the end of the talk I can come back to this. But this is what I want to say about problem A. Now let me talk about problem B. So let me start with the Sn symmetrical. So the first significant result on bounding capital values for symmetrical was obtained by survey Pham and Nathan Luller in I think in 96, where they put the following. So suppose that you look at the G, so G is homogeneous, right? And then look at the case where your G is homogeneous. So we mean that this is the product of these two sides of the same length. So like product of lengths of the same size and the n side. So then they show that if you fix the n and you let n to infinity, then you can prove that chi G is then divided by chi 1 to the 1 over n. And that will be best possible. But unfortunately, they have to have something like a little over 1. So this something tending to 0 when you enter to infinity. And this is a highly marginal result. So like the 12 years later, Larson and Pallet, they vastly generalized the result, and so it's 2008. Then they show that the same true. The truth is if you G as well, maybe it's not like every cycle have length m, but let's say that you have only n who some little of 1 cycle of length less than n. Okay. And so I think this is a paper in Sodes where the book is kind of bound and we were able to use a lot of arguments like on the application that I mentioned. Okay. So okay, so now let me talk about some more recent results on problem B. And from now on, I'm talking about the two sides or maybe the plus and group. So let me introduce like a convenient framework that you can use when you work with a group of data type like chain and field. Of course, you can try to use the geometry like the context geometry like the form and linear form and so on and matrices. But maybe the more convenient way to work with them is the following. So we are going to view them like finite roots of lead type. Well, so you look at finite error of lead, right? But more concretely, what you do is the following. So you have to have some G, which is a, let me say, a kinetic, reductive, under group, over, let's say over FE, then you have something like a morphism of G, which is called a Frobenius morphism. What does it mean? It means that this is a morphism of Arabic group, which is selected, and then you want it, you want the set of the fixed point with finite. Okay, then your group G becomes the fixed point. This map. So let me give you one example, like so maybe I'm going to skip this example. So let's say that you look at the skip G to be the SL2. Then you can say you take the map F to be the map that send A matrix. The send A entry of your matrix to be the Q power of it, right? Then you see that this the skip G F our final group is going to be directly the two matrices over the FQ. Right? Okay. Right. Then so now suppose that you have L, which is an X table, a Levy subgroup. So a Levy subgroup can symbolize a limit torus, and then you have to say that your L is called split. If your L is a Levy of an F table parabolic subgroup. So when you have a Levy subgroup, then it's going to be a Levy subgroup of some parabolic subgroup, but then because I want to have the condition that is the parabolic subgroup to be F table, then you see that this is not a Levy subgroup is the F table. So let me go back to this example. For instance, if you so in this example here, so you can see that if you look at the set of the diagonal matrices in your G, then you can see that this is the fixed point subgroup for some split Levy. So it's torus. But on the other, you have something that we call the consider torus, which is a subgroup, like another subgroup for another example where the order is P+1. So this one has order P-1, but this one has order P+1, and this one is non-split. Okay. Right. And now, if you give me an after the Levy subgroup, then let me define something that I call the alpha invariant. So let me define the alpha for this. So let me define the alpha of NF to be something like this. So I'm going to define this to be 0 if your L is a torus. Now, if your L is not a torus, then you depose an element there. So then what you do is you have to look at the maximum of the ratio between the dimension of the class of the element U in your Levy is divided by the dimension of the class, but in your G. What the U here? U is let me see. U is any unipotent element in the finite Levy. So U is unipotent. So okay. So if you look at the closure of it, then you get a time parameter, then you define the dimension of it. But here you look at inside the levy, and here you look at the inside the cover too. Okay? And now, of course, I think I already the problem B, but the way that I define to be alpha, that's probably it has something to do with the problem B, right? Where I want to find the alpha invariant, the alpha to be kind of bound, right? And now with that, or maybe I should give you some example. What is the value of this alpha? Okay, so another example is that. So if you look at your D to be Zealand, oh, then you can see that this alpha is going to be bounded by something like n-2 over n-1. But if you take your G to be something like E8, then this alpha is going to be at most 17 over 29. And you can guess that this is attained if you look at the levy which has a type of E7. So it's like a centralized one-dimensional force in E8. So what do we do with this alpha here? So here's a theorem. We need you to Raman with the what is it? Financial health. So we put the following. So there is this and his unit function f from the integrals to the integrals. Start there with the following. So suppose that your G is connected deductive another book, where I have a condition that I want to make sure that so I want to make sure that if you look at the right of the direct couple, the code will be R for put on the same symbol. And now I look at my final group. And suppose that you give me some element with G in your final group. Start there. When you look at the centralizer of this little element, that is containing some levy for a proper. Levy. Yeah. Okay, so and here what I mean by this thing. So suppose that we have this, then your GPRT is going to be bounded by GPRT1 to the alpha. The way that I define it. But now we come back to what Milan said. What I have is a concept neutrality. So you see that this thing here doesn't. I mean, this thing doesn't depend on the size of the thing Q, right? But it depends on the right. But this thing controls the growth of your scatter value when you let your Q grow. Okay. Oh, yeah. I forgot one more assumption that the P, the characteristic that I used to define my group has to be a good prime. So for type A, everything is okay, but for type B with COD, then P cannot be good. Okay. And okay, so that's the theorem that and now
Can I ask if you were saying GON?
yeah,
And you have a standard level, like the level of standard parabolic, so
Yeah.
function of diagonal matrices.
so
what is the alpha then? So it's a number between whatever, let's recall that n minus 2 over n minus 1, but perpetually is an explicit form.
Yes. Yes, okay, yeah, so let me go back to that. In fact, this is the so I can give kind of like a sort of answer to your question. So yes, right. So you can look at the effect. So Theorem, right?
Mhm.
And your N is like you can N1 or you can let's say, M, right? And let me see, I'm going to do them this way, right? So the answer is, we don't know the exact answer to your question, but what, so I can give you a formula, but then, I think it's something like is at most, and let me see, and 1 over n. And then I have a low one, which is something like I think it's n1 minus 1. Okay, I can look it up, but I mean, so there's a formula, but it's like you have to optimize over like some distinct object, and we don't know what is the exact answer to this. But if you give me the lady where all the n are the same, then what is exactly equal to n1 over n? Okay.
And why do you want to define the alpha as quotient of 2 dimensions as opposed to the size of the conjugacy class in the
Yes,
in LF
right.
divided by the size of the
Okay,
conjugacy
yeah.
class in GA?
Okay, so the reason is, so this is you are talking about the proof of this theorem. So how do I prove this theorem? So the idea of the proof is that so the condition on the centralizer tell me that whenever I have the character, then if I want to evaluate type G, then instead of that I can do the so-called the Harshchandra restriction of the character. So or Harshchandra translation, if you like. Okay, and then this ratio here. Okay, so this comes from the so-called the notion of the uniform support, Rustic definition of the uniform support of the character, and then and there's a dual notion which is called the wave transit. Wave transit of your character. So right. So this is dual notion, meaning that when you have a character, then you look at the undiscovered dual of your character, and so you take the European support of your undiscovered dual of your character. So that will give you the wave transit. And now this kind of object control the wave transit of your levy of your character over the levy, and this is in your group. And so the main proof that I have to do is that I have to control the growth of the wave transit when I do the Lucid inductor and Lucid restriction. So yeah, okay, so that's why I have to divide one by another. So I hope that I get some idea. Yeah, right.
And this formula, so the formula that you wrote, n1 divided by n.
Yeah.
So n1 was simply the number of simple roots, maximum number of simple roots that are connected in a Deakin graph of that levy. So that's true for any finite group of simple type, like distinct for EA. Is it the same formula, like the number of simple roots of the levy that are connected in the graph divided by all simple roots, or it's more than that?
I think it's more than that, because well, if you move from type A to type B or C, then it's always only like more figures. Yeah. Okay.
So it's not just maximal.
Yeah. No, it's not. Yeah. Okay. Right. So let me make some comment, and you can see that the restriction that I have to assume that you'll be good prime, because like all this theory about wave transit, they are working well only when you have the good prime. Okay, so here we are relying on result of Lustig and Kavanaka and also the big paper of the existence of this and of this wave transit. Now the other thing that I want to but now let me make a comment about this. So how ultimately this formula. So now if you don't care what the function f of r, then this constant alpha, then is the exponent alpha is open in many cases. Meaning that you pick the right variable and you let the sign of people can be fitted, then you can get some pattern where the ratio is really like cat one to the answer. Yeah. But what is the F? The F of I is like well, it's something like the square of the order of the value. So it's something like this. So it's a big constant. But there are examples to show that you cannot. So it should be at least like the square root of the something like it should be at least square root of the r plus 1 to 4. So maybe we go from the power 1 has to be square. So it's not that here. I mean it's not optimal, but it's close. Okay.
In that formula for million company, they just get off one. So they don't really have an estimate of.
No, yeah. What's
So
the
they
story
just
about?
have a large constant. The 4 million then after that.
Yeah, the formula and the rule of the last yeah. So the point that they are bound are very good, but then you have to, but they are only asymptotic one. But where this formula here that everything is exclusive. Yeah. But the point that maybe like maybe the important restriction is that that here I have the condition that the label is split, and this is reason that when I yeah, again I'm talking about something that is actually the theory because I'm talking about the proof. So maybe I'm going to write here for me then. So the idea that whenever you have your G like this, then this is exactly the so-called the Arishchandra restriction of your G to L account. And then I evaluate the G. Yeah. And so okay, well, so when your N is split Levy, then you have the Arishchandra restriction. Now if your N is not split Levy, then you have the displacement, which is the lucid restriction. So you still have this formula here. But to control the wavefront set and everything, then it looks to be very hard. You have to do it like at the geometric level of the character sheet. You cannot just do the yeah. So we put this theorem, but then and then yeah. So we work on it for a number of years, and then unfortunately we can improve it. So this is the result. So this is the which due to my former photo, J. Taylor, and with myself. So we remove. So let me put it this way: the B and ST, so B for the room capital, the room capital, and so on. For non-free so, but then we have to compensate for it. So we can assume that your N is not a split daily, but then what you need is that you need the center of the connected. So for instance, if you work with PLN, then linear is okay. But if you work with the SLM, there is not good. Yeah, so the center is connected. But there is a way to go around it in the current problem. So okay, so now if we're going to assume that your G is the group in a good prime, and then your element is has a property that the centralized contains some probability. So it's like so it's something equal the element is not isolated. Then you're okay. But the question is, what if your centralized is not containing any variable? Then, and of course, for instance, you can think of something like, of course, the identity, right? The centralized is the enthalpy, right? But what about the U-bound element? So e.g. U-bound. And if you think about it, then if your element is not shared U-bound element, then you can never put the centralized inside any global label something. Okay. So So how do you, but can you see like approach this problem? So now, so let me talk about another approach to this problem. Another approach. So this is due to running. Nothing. And so it seems that the there's a way to deal with this problem. If you assume that so let's assume that the degree is not too large, or maybe the size of your class is not too large. Then the other approach that you have is that you can define, we can use this so-called the level theory. Level theory for your calculus. So so the two ingredients that you need to define the level is that so we have to rely on the level theory, and also we need to use the Rosenhaus duality. So let me just define the notion of the level. So maybe let me start with the Sn. Then you know that you can classify the character of this group by partition, right? So you write lambda. So lambda is a partition of your n. Right? Okay. And so then it turns out that you should define the notion of the level of your chi to be m if your lambda is like n minus m, and then and so for instance the level 0 it means that you have the achieve limitation, right? And then you look the natural limitation n minus 1, then the level is 1, and so on. And you can see so n is 0, then you can see the degree of it is 1, m is 1, then the degree like n minus 1, if m is 2, then this is like it is n times n minus 3 over 2, or n minus 1 and minus 2 over 2, right? So that will tell you that somehow the level control the growth of the degree of the character. Okay. So how do you define it for the group of B type? Then so let me give you the example and XQ. So here you can see that you can also look at the action group or the action model which is X2 to the X, right? Then you can let your group act on this, and then you can count how many points that you fit, right? So then the permutation character. Let me put tau here. So tau G is just a number of G fixed vectors in your B. Okay. So the degree with include the N. And now I can define the level of your character. So you going to say that the level of your chi is J if J is more or less such that your chi, when you look at the scalar product is told the J is not 0. So this means that your chi is in the continuum of this J power 2. Okay, and so this is some example. So if you look at the achievement character, then you can see that the level of your chi is just 0. But if you so for example, you have some U-model character between Q to n minus Q over Q minus 1, then the level is 1. But if you look at the standard character, then the degree is like q to the n times n minus 1 over 2, then the level of this is going to be n minus 1. Okay. So so what do you do with the level? Well, so
Sorry, can I ask about this power of G?
yeah,
So this is, so you're looking at G minus identity and the kernel, so isn't that just a vector space? Isn't power of G the cardinality of a vector space?
Yes,
That's the
that's-
kernel of G
right,
minus
right.
one?
You can say that this is a q to the dimension of the kernel of the.
Yeah, okay.
Right. But
Mhm.
see, here's the fun question. What do you think? What do I do if I go to the SU and Q?
Mhm.
Can you guess what is the replacement for this character?
Right. Well, I don't know, something that's preserved some.
But this
Right.
something called the annular duality. We say that if you want to go from the data group to the utility group, then you replace Q by the minus Q. And this is exactly what I do. So you can think of SU and Q like SM and over the field of minus Q element. Probably understood, yeah, I can agree with, yeah, okay. But so this is the so-called the annular duality, which was proved by Kamana and Buchhaus. Anyway, so then the result of Uranic and Larsen and myself is the following. So first we relate.
Can you say a bit more, what does that identity mean?
Pardon?
Can you say, what does that identity mean? Or does it mean that if you have a character formula, you formally replace Q by the negative Q word?
Okay, yeah, right. So the whole thing is the following. So for instance, like if I want to do this probably then you have to look at the mean function, which is the like the so you look at the generalized the linguistic characters, and then you look at the values of those characters at the of those version characters at the ubiquitous element, and then so you have like some formula depending on Q, and now then the second is that if you know that I mean you have the same classification of Euler classes for GLN and GUN, right? So in that formula you replace your Q by minus Q, then you get the mean function for GUN Q. But you're right. I mean, of course, that wouldn't make sense. What is in here, right? So let me give you the exact formula for the character I use in the case of U and Q. So the character I use is the following. What I have to do is I like minus Q to the dimension of the kernel of G minus 1, right? Over Q squared. But then I have to compensate for the sign. So that's why I have to put minus 1 to the end here. Okay, and this is actually a true character of G and Q. Well, even though like it took a minus Q, but then this the degree is same to the end. This is an actual character. Okay. Right. Okay. So now so now I can formulate the so-called the GMT bound. Okay. So we say the following. So for only epsilon. So it actually looks like calculus. This some delta is 0 and 1. Got that. Your G is like y is equal root of lead height. And if the centralizer of your G, if G is some element in the group, that the centralizer has in the order equals G to the delta, then you can say that type 1 and type G is then bounded by type 1 to the epsilon. Okay. And so like probably 22 plus. And let me give you one example. So let's say that if you take your G to be like SRN and Q or SU and Q, then I think if your epsilon is something like 8/9, then I can take your lambda to be something like 1/12. Okay. Right. So I gave you this bound, which is due to measurable chemicals and company, and then this bound GNT, one glass and Tiep bound. But each of these bound, they have some conditions, right? For the BNSC, that I have to have some condition that the centralizing of the element is containing some probability, right? And in this bound, that I have like if you want to centralize we bound by something like this, right? Okay.
So how does the assumption there depend on epsilon? I cannot digest for every epsilon there exists a delta.
Depending on epsilon.
Only the epsilon delta.
Yeah. So whenever if you want to make sure that your chi G is at most chi1 to the epsilon, then if you centralize it, it's not big enough, then you have this. Okay. So, right. But again, like when we are teaching calculus, right? This is diffusion of the limit, right? And you have to make sure that our students have the right order epsilon delta. Well, this is the right order in this form, in this theorem. But for the application, what I really want to do is I want to solve delta and epsilon in this theorem. So yeah, so now I can say that if I know the centralizer is less than G to delta, can I have an epsilon? So then I have the chi G equal to chi1 to the epsilon. So that's another rule here. Can we swap epsilon and delta in here? Okay, because that will make like my life much easier. Okay, so now let me spend time to describe like one of the one of the most recent results which overcome all these differences like in the BLSC bound or in GMT bound. So this is the theorem. Did you do Michael Larsen? Myself. So also. Okay, so we put the following. So this is an explicit constant. You can see that for all the one is simple root of p type in any characteristic for all the element so the G here for all the element G in the root you have a uniform bound on the capital value. So the chi G is going to be bounded by chi1 1 to 1 minus C times log of the side of the class divided by log of the group owner. Okay. So okay, and let me make some remark here that so there are like you can show that there's some kind where chi G is at least chi1 to 1 minus 6 times log of. Okay, so after this constant C, then the formula that I give you is open. Okay, so this means that this ratio here is the right, you know, it's the right constant to control the growth of your constant value. And also, so how do we relate this ratio to the support that I gave you before? So if your G is equal to right n of dimension n, then you can see that if you look at these two notions, these two ratios. So this is like omega of the support of the divided by n. So it means that one is bounded by the other. With the computer science formula notation. So that show you that, okay, so it means that up to C, up to kind of see that the NC bound is okay.
And how does this compare to the theorem about Rudolph?
Right, so. Yes, so this is the nature, this C here. So, on the one hand, so maybe the answer is the following. These two different results, they work in different realms or ranges. So this one is good, if I think this one is good if your Q is large enough compared to the right. Where this formula is good if the right of your root is larger than the Q. Okay. And since you don't ask about it, I want to tell you what is or how tiny C is. But maybe I can tell you what is C, right? C is about 10 to the minus 29. It's a very tiny one. So like that. When they talk the Peter science say that, well, said that, well, you have to have your right to be very large to swallow this tiny candle that you have. And now let me tell you why I have this tiny candle. Oh, I actually do like this because I'm so so let's talk about the proof and the idea of the proof of the anti-bound. And you can see that, so I started by talk by saying that if you can prove some kind of bound, then you can solve a problem like some kind of probabilistic problem, right? Or random walk and so on. But so here we reverse the order of thing here. So here we have to use the probability theory. Theory to solve a representative theoretic problem. Okay, so what I do with the problem? So if you give me this element G, right? Okay, then so how do I bound the category? So what I do with that, I'm going to do the following. So I'm going to iterate my problem, and I'm to look at the like the product of. So I'm going to choose my counterweight of your G randomly uniformly. I take M of them. So then look at the product of M random counterweight, and then I look at expected value of this. Okay, and the formula then is going to be type T to the M divided by type 1 to the minus 1. Okay.
Expected values.
So the x1, xm, the r n independent variable. You choose these.
Okay.
Yeah. Okay. So and the proof of this, you can prove it using the first formula that I gave you, the first formula. Okay. But now, so then what you do is that you prove that when you look at this kind of random product, then they mix very well. So we put the mixing, so you put a mixing theorem to say that with high probability, this product is going to land in a small class. To which I can apply the reality bound. So our this result depend on the result of 200 and myself. So and you see that okay, so you start with a large class, then you do this kind of random product, then this kind of chance that you want to land in a small class. And then to the small class, it means that to this product, you have good bound on this. But then look at this, then good bound on this means that you get good bound on kind of cheap. But in fact, we have to do it in several bootstrap. Okay, so we cannot just bootstrap our element right away so that I can apply the GMB bound. I have to first I look at some mid-range, I can bootstrap that one, but I will then rebound, and then for if you give me element, then I bootstrap that and then to get into the mid-range. And that's the idea of the book. Now I think I already went over my time, so I cannot tell you that the question that I raised before, like I want to have a linear upgrade of the raster chart and Tiep bound, and also the task that I want to solve X on data, they are all achieved by this empty bound. And also I think recursion to the random walk on that we can put someone. They can put a container of robots or the graph and also some of the containers of market.
I've already asked, what is the expected value? It's G to the maximum.
Okay, so I mean like so the x1, xm, they are the n random variable on your group, right? But like so I treat them independently and uniformly. So then this give you like okay, so then you have this problem that you another random variable, right? And then you look at expected value. Now, what is the expected value? It means that you so you pick some element, then you look at the probability that you obtain that element. You multiply the factor of that element by the probability you get. It's okay?
Yeah.
So is the chi the expected of chi i's as random variables? Or
The chi?
what is the relation of the chi and the chi i's as random variables?
Oh, no, this is not chi. This is x1, xm.
Oh, this is x. Okay.
Yeah. Yeah, right. Sorry. So these are the m random variable on your group. Yeah. So I just pick like so put it this way. I pick a like a product of m random conjugate of your element, and I ask myself most of the time what do I get like out of this product, and it turns out that most of the time you are going to land in the small class, but why that and the small class is yeah. But then,
Should this be a summation over chi's or
pardon?
should it be a summation over chi or
No,
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 just-
there's no summation.
Okay.
So that's the beauty of this formula.
yeah?
Yeah.
So how does the chi relates to that left hand side? I didn't see the.
Yes, you are completely right. Yes, I think I asked.
Ah.
Yes, thank you. Yeah, sorry about that. Yeah. The estimate value of the capital value in that random product. Yes, thank you. Yeah. And but let me explain why that you see that if you look at your book, right, most of the elements are regular. Right? So yeah, like some regular semi-simple element or regular element, right? So maybe we will pick that 99% of the elements are regular. So if it's very bad element, if I take the product of them, then at some point I will reach this the good element, and that's the the qualitative implication of this formula. Yeah.
Any other question? And let's thank Pham Tiep again. Hmm? I'm not. Yeah, I'm not.